A very warm welcome, my dear students. In today's lesson, we will talk about the Gauss Law. Now, in order to understand Gauss Law, we have to first understand a few basic terms like the area vector, the electric flux. So here we start with the area vector. Now, area vector is a vector which has a magnitude which is same as that of the normal or the usual area that you calculate, but it will also have a direction. So what is the direction of your area vector? Now the direction of your area vector is along the outward drawn normal to the area element. So suppose this is the surface that we are dealing with. So I draw a normal. Normal means it's supposed to be perpendicular to the surface, and then it is outwards. So the direction of your area vector is simply an outward drawn normal. Area wise it's the same, so magnitude is pretty much sorted. For the direction you will always take an outward drawn normal. This is about area vector. Now let's talk about the electric flux. Now electric flux firstly is represented by phi, and it is simply the amount of electric field that is passing through a particular area of a conductor or a surface. So we can also say it is the total number of electric field lines that are crossing through the surface in a direction normal to the surface. See, mathematically the flux, which is represented by phi, will be equal to E dot ds, where E represents the electric field, ds is the area vector. Now this is the dot product. If I open this up, you can also say that this is E ds cos theta, where theta represents the angle between the electric field and the area vector. So over here, this is my area vector, this is my electric field over here in this particular direction. Therefore, this represents theta. Now over here, the integral that we have to take, it's a surface integral. So whatever surface that you're taking, make sure that it's a closed surface. So in general, we can write our electric flux as E, the electric field, times the area vector times cos theta, where theta is the angle between electric field and the surface area. Fine. This is about electric flux. We should be able to calculate the electric flux through any surface. In one way, it is simply measuring the amount of electric field that is coming through a particular part of the surface. Now, we will try and solve one question based on electric flux here. So the question says, if the electric field is given by 6i cap plus 3j cap plus 4k cap, calculate the electric flux through a surface of area 20 units lying in the YZ plane. Now, I already know my electric field over here. It has been given to me as 6i cap plus 3j cap plus 4k cap. If I talk about my area vector is being given as 20 units in the YZ plane. So look, if this is the YZ plane, let's say that this side is the Y and this is Z plane, then the part or the vector that would be normal to both YZ would be along the X, because our area vector is always an outward drawn normal. So obviously if this direction is Y, this is Z, so this has to be X. So my area vector would be along the I cap. So it is 20 I cap, whatever units they are talking about, let it be the same. Now for flux, I know that flux is equal to the dot product or the scalar product of electric field and the area vector. So therefore my flux can be written as 6i cap plus 3j cap plus 4k cap times, or the dot product with 20 I cap. Now for the dot product, you know that I dot I is 1 and I dot j or k is going to be 0. So this is something that we learned in class 11. So I know that 6i dot 20i is the only one that will give me something. So I into I is 1. So this comes out to be 120 units because they have not specified the units for the area, so I just take it as units. So 120 units. In general, if you talk about the flux, the unit for flux, if you want to talk about, it would be like, if I take everything in SI units, it would be Newton meter square Coulomb minus 1. So now further moving on to the Gauss law itself. So Gauss law simply states that the total electric flux through a closed surface, which is enclosing some charge, is equal to 1 by epsilon naught times the magnitude of the charge that is enclosed. So mathematically, this means that the flux through any surface will be equal to the charge that is enclosed. If I say that Q is the charge enclosed in the surface, divided by epsilon naught. Now, since my flux is also equal to the surface integral or the closed surface integral of E dot ds, therefore, the same equation can also be written as E dot ds equals to the charge enclosed by epsilon naught. Over here, whenever we want to apply Gauss law, we always have to apply it to a closed surface. Now, since I have to apply it to a closed surface, so there can be situations where you do not have a closed surface given. So then you're supposed to choose your closed surface. So that surface that you choose is what is called your Gaussian surface. Now, while choosing your Gaussian surface, you're supposed to take care of two things. One, that the electric field intensity at all the points on this surface should be same. So the first point would be that the electric field intensity of your chosen Gaussian surface should be same at all points. So electric field intensity at all points on the surface should be same. So this is one thing that you have to keep in mind while choosing your Gaussian surface. And the second thing that you will keep in mind while choosing your Gaussian surface is that this electric field should be generally normal to the surface. And it should be along the normal to the surface. So if you keep these two things in mind while choosing your Gaussian surface, then you'll never go wrong with it. And also, of course, it's a closed surface. So it would be something like a sphere, maybe a cylinder, or a cube, or a cuboid. Something of that sort has to be chosen here. So I hope you understand the Gauss law and the Gaussian surface here. So we will try and answer one question related to it. So a spherical Gaussian surface encloses a charge of 8.85 into 10 to the power minus 8 coulombs. We have to find the electric flux passing through the surface, and there's a second part which says that if the radius of the Gaussian surface is doubled, how would the flux change? So if we want to calculate the electric flux, then electric flux is given by the charge enclosed by epsilon naught. As per the question, the charge enclosed is 8.85 into 10 to the power minus 8 coulombs. And epsilon naught value we already know is 8.85 into 10 to the power negative 12. On simplifying this, I get 10 to the power 4. The unit for flux here would be Newton square, meter square, Coulomb minus 1. So this is directly by using the Gauss law. Now for the second part, since they're talking about the radius, if I double the radius, okay, now on doubling the radius, actually there will be no effect on the flux because as we saw from Gauss law, my flux is independent of the radius. It is only dependent on the charge that is enclosed. So because it is independent of the radius, therefore there will be no effect on the flux. The flux would remain the same. So I hope this question is clear. Now further moving on, let us talk about the proof of Gauss law. Now in order to prove Gauss law, let's say that there is a charge Q lying at this point O, which is basically the center of a sphere, and the radius of the sphere is r. Now if I talk about the electric field on the surface in here, so electric field on the surface of the sphere can be written as simply kq by r square, and if you want I can put a unit vector here, r vector, for the direction. As it is, if it's a positive charge then the direction of electric field would be outwards, else it would be inwards. Now as per the Gauss law, because we are trying to prove the Gauss law, therefore we are trying to prove that the flux has to be equal to the charge enclosed by epsilon naught. So in order to prove that my flux is equal to that, I have to first calculate the flux. So I know that d phi would be equal to E dot ds. So E or EDS, I can also write cos theta. So over here, from the above expression, I know that my electric field is kq by r square. ds is simply the area of the small part for which I am writing the flux, and later on I can integrate it for the whole part. Theta in this situation is going to be 0 degrees because my electric field and the area vector make 0 degrees with one another. Cos 0 is 1. So from here my d phi simply comes out to be kq by r square times ds. Now if I want to find out the electric flux due to the whole sphere, I need to integrate this expression for the whole sphere. So from here phi becomes k is k and q r square, all of these are constants. I take them out of integration and I have the surface integral of ds. Now since this is a sphere, therefore I can say that the flux is equal to kq by r square. The integration of ds, the area, the surface area of a sphere is going to be 4 pi r square. So this is kq into 4 pi r square. From here, r square and r square get cancelled and I further get my flux as, now I'm opening the k, so I'll write k as 1 by 4 pi epsilon naught times 4 pi, and there is a q from the numerator. So 4 pi and 4 pi get cancelled. From here you can see that your flux comes out to be the charge, that is q enclosed by epsilon naught, and this is exactly what Gauss told us. As per the Gauss law, we know that the flux enclosed or the flux through a surface is the charge enclosed by epsilon naught. Also, we have proved the Gauss theorem here for a sphere, like we kept the charge at the center of a sphere and we proved it. But instead of sphere, if I had any other closed surface of any shape, then also we can prove the Gauss law in the same way and it would give us the same result. Now, I hope this is clear. So further moving on, let us try to derive the Coulombs law from the Gauss theorem. Okay, so in order to derive this, let's say that I have a charge q1 which is lying at this point A and I have a charge q2 lying at a point B. Now they are separated by a distance r. If I want to talk about the force that is experienced by the charge q2 due to q1, so the force experienced by charge q2 due to q1 can be written as q2 times the electric field. Now this electric field that I'm talking about is the electric field that is coming due to charge 1. Charge 1 has an electric field which is external for charge 2, and charge 2 has an electric field which will be external for charge 1. Now, as per the Gauss law, I know that the flux through a closed surface is going to be q by epsilon naught. I can further write this as E dot ds is equal to q by epsilon naught. Now in this situation, if I am writing the flux for this small part over here, you can again see that my E and my ds vector, they both are parallel. Now since these two are parallel, therefore theta here also is 0 degrees, and we already know that cos 0 is 1. So therefore this expression only becomes E ds, cos 0 is 1, so we'll just omit that, and this is supposed to be equal to q by epsilon naught. Now E is constant on the surface, so I take that out of my integral. So I'm left with the ds integral equals to q by epsilon naught. Now the surface area of a sphere is 4 pi r square. So this is E into 4 pi r square equal to q by epsilon naught. From here the electric field comes out to be 1 by 4 pi epsilon naught q by r square. This is the electric field due to the charge q1 which is lying at the center. Okay, now further if I talk about, I can substitute this value of E in equation 1. So substitute the value of electric field in equation 1. Now on doing that, I'll get my force as Q2 times 1 by 4 pi epsilon naught this was Q1 because that is the charge enclosed inside this affair. So I should have written it as Q1 from the beginning itself. So this is Q1 here upon R square. So my force comes out to be 1 by 4 pi epsilon naught can be written as K also, or if you want you can write it as 1 by 4 pi epsilon naught itself. So it is 1 by 4 pi epsilon naught times Q1 Q2 by R square. And if you remember, this is exactly what Coulombs law tells us. So we can also write it in another form. We can write it as K Q1 Q2 by R square. Both equations are correct. But this is how we derive Coulombs law from Gauss law. This doesn't come as a direct derivation as such. It's not even present as a derivation in the book, but sometimes they give you a question that derive Coulombs law from Gauss theorem. So it's not exactly a derivation, but they put it in the question form. Now, further talking about the electric field and the Gauss law, we will try to solve one particular question based on the Gauss law. And let's just quickly look at the question. So the electric field components due to a charge inside the cube of a side 0.1 meter are as shown in the figure. Then Ex, that is the electric field along the x direction, is alpha x, where alpha is 500 newtons per coulomb meter. Ey and Ez are 0. We are supposed to find out the electric flux through the cube and the charge inside. Now, so firstly, let me try and show you something over here. So we have electric field only in this direction and there is no electric field in the y or z direction. Okay. Now if we try to figure out the area vector for this top surface, then it would be like this. Now this area vector and Ex are perpendicular. Because these two are perpendicular, therefore for this particular side, the topmost side, theta would be 90 degrees and cos 90 is 0. So this side does not contribute to the flux. Similarly, the lowermost side also do not contribute to the flux. This front side would have the area vector again coming in the z direction, something like this. Even this is perpendicular to Ex and hence this side also does not contribute. So the only two sides which contribute to the electric flux in this particular situation is this side, because this side has the area vector coming in like this. So here your theta is 0 degrees. So we'll just call this as E right, or we can say that this is the flux due to the right surface. And there would be flux coming in from the surface over here. So this one will have ds vector this way, and therefore its theta is going to be 180 degrees. So the flux that is coming out through this, I can call it the flux due to the left surface. So only the left surface and the right surface contribute, because for all others the area vector is perpendicular to the electric field and hence the flux through them would be 0. So now if I want to write down the electric flux through the left surface, first let us try to write down that. So the flux through the left surface, we know that flux can be written as EA cos theta or ES cos theta. You can represent area by ds or dA, that's your choice. So further over here, if I talk about the flux due to the left surface, my electric field. So electric field is alpha times x, and alpha is 500. So 500 times x. X for the left surface is 0.1. So this is simply 0.1, or I can just take it to be a for the time being, and I can substitute this later. So this is for the left side, and then the area for this particular, because it's a square, so let the area be a square. I have assumed that this side is 0.1, that is a. Okay, now cos theta, we already know that this is going to be cos 180 degrees. So this flux due to the left surface comes out to be minus 500 a cube. Now similarly, let's try to write down the flux due to the right surface. Now the electric field for the right surface is also 500, but now this one is 500 times the distance for the right surface, you can see, is 0.2. It is not 0.1. So this would be, you can simply say that it is 0.2 times a, or that's your choice if you want to just double it. So I can say it is 0.1, or I'll say that this is 2a. I think that would be better since we took a as 0.1. So I'll take this as 2a. I'm trying to write everything in terms of a so that later it's easier for us to subtract and then directly put in the value in the end. So this is 0.2, a is 0.1, so it is 2a. And then over here the cos value, right, cos would be here 0 degrees because it is parallel. Now this comes out to be 1000, and sorry, I forgot to take in the area would be a square as well. So 1000 a cube, and cos 0 is just 1, and this is positive. Now the total flux will be equal to the flux due to the right surface and the left surface, so we'll have to subtract them since they are in the opposite direction. So 1000 a cube minus 500 a cube, this gives me simply 500 a cube. Now I can directly substitute the value of a, which I took as 0.1. So 500 into 0.1 cube gives me a value of 0.5 Newton meter square Coulomb minus 1. So this is the total flux through this whole cube. So I hope you understood this part of the question. Now, further, if I want to find out the charge that is enclosed inside this sphere, so for charge, now I can directly use the Gauss law. I know that flux would be equal to the charge enclosed by epsilon naught. So if I want to calculate the charge enclosed, all that I have to do is I have to multiply epsilon naught and phi. So epsilon naught is 8.85 into 10 to the power negative 12, and my flux is 0.5, which we already calculated. So on multiplying, I would get my charge as 4.425 times 10 to the power minus 12 coulombs. So this is the total charge that is enclosed. So with this, we are done with the question. I hope you understood the Gauss law, the area vector, the flux, and how to apply all of these. If you understood whatever I taught you today, then please subscribe to my channel and do like and subscribe. Thank you for watching.